Jai Hind students, welcome to my YouTube channel. Students, always have faith in your abilities. There is something inside you which is much greater than any hurdle or any obstruction. So have that self-belief and then no one can stop you from achieving success. So students, with that, let's begin today's session. And today we are going to discuss a very interesting topic, which is dot product. It is also known as scalar product. Actually, it is also known as inner product. So let's start with this particular topic, right? Dot product of two vectors. First we'll discuss its definition, then we'll discuss its properties along with various examples and some basic numericals, right? So, dot product. Dot product of two vectors, A vector and B vector. Suppose these are the two vectors. This is A vector and this is, suppose, B vector. And let us consider the angle between A vector and B vector be theta. Students, the dot product or the scalar product or the inner product of two vectors A and B, which are inclined at an angle theta, is defined as the product of magnitude of the two given vectors and the cosine of the angle between them. So this represents the dot product. This is the representation of dot product, or it is the representation of inner product. It is also known as inner product or scalar product. So students, the dot product of two vectors A and B is defined as the product of the magnitude of the two given vectors and the cosine of the angle between the two vectors. So this is how the dot product is defined. Now, why it is also known as a scalar product? It is because the dot product of two vectors is always a scalar quantity. The right hand side, which is magnitude of A multiplied by magnitude of B and cosine of the angle between A and B, it's a scalar quantity. No direction is associated in the right hand side. So that is the reason why the dot product or the inner product of two vectors is always a scalar quantity. Okay students, now we will try to define the dot product in some alternative way, right? Let's consider first case. I'm going to draw the same diagram. This is B vector and this is point 2 and this is A vector. This is A vector. And we have considered the angle between them to be theta. Now what we do is, we will try to resolve or rather split A into two perpendicular vectors. So this is A vector. Its two component would be one along the direction of B, which is A cos theta, and the other perpendicular to that is A sin theta, right? We are not bothered about A sin theta component. Let's consider only the component of A, which is along the direction of B. That is, what we get is, if you draw a perpendicular, then this component, it would be equal to A cos theta. Am I clear? So students, A cos theta is the component of A along the direction of B. Another component of A would be along this direction, which would be A sin theta. But here, we are not supposed to make use of that component. So let's avoid that. So we have resolved A into this component along the direction of B, which is A cos theta. Now look, A dot B. It may be written as B into A cos theta. We can easily write it like this. So how to define it? It is defined as magnitude of B multiplied by magnitude of component of A along direction of B vector. So this is how you can define the dot product. So the dot product of A vector and B vector may be defined as the product of magnitude of B vector and the magnitude of the component of A vector along the direction of B vector. So this is another way of defining dot product of two given vectors, right? So let's try the case 2 as well. Again, let's draw the same diagram. This is B vector and this is A vector, right? The angle between them is considered to be theta. In the first case, we have resolved A along the direction of B, right? Now what we do, students, let's resolve B along the direction of A. So the component of B along the direction of A would be B cos theta. If you drop a perpendicular from here, it will be B cos theta, and the other component will be B sin theta. No use of B sin theta, so I am not drawing that component, right? So B cos theta here, it's the component of B along the direction of A, right? So here, A dot B may also be written as A multiplied by B cos theta. So what you get is magnitude of A vector multiplied by magnitude of B vector along the direction of A vector. So this is how you can define dot product. So students, dot product of two given vectors may also be defined as the product of magnitude of one vector and the magnitude of the component of the other vector along the direction of the first vector. So these are the ways in which the dot product of two vectors may be defined. And students, as we have discussed, dot product is also known as scalar product. It is because the dot product of two vectors will always give us a scalar quantity, and that we'll discuss in properties. So we are over with the definition part. Definition of dot product of two vectors is over. Now let's discuss some of its properties, which are very, very important, right? So let's start with the first property. Dot product, it obeys commutative law. We'll prove these properties as well. Let's first discuss it theoretically. So properties of dot product. First property is it obeys commutative law. It obeys commutative law. That is, A vector dot B vector is equal to B vector dot A vector. Because as you are aware, the dot product of two vectors is a scalar quantity. So you can either write A dot B or B dot A. The result would be same. We'll prove it mathematically, right? Second is, it obeys distributive law. It also obeys distributive law. That is, A vector dot B vector plus C vector. It will be given by A vector dot B vector plus A vector dot C vector. This also will prove it mathematically, right? So dot product or scalar product obey both commutative law as well as distributive law. Third, as I have already mentioned, the dot product of two vectors is always a scalar quantity. And this is the very reason why dot product is also known as a scalar product. Dot product of two vectors is always a scalar quantity. Let's discuss some examples that will convince you. First example is work done. Work, as you are aware, it's a scalar quantity. It is given by the scalar product of force and displacement. Right? So, if this is force acting on a body, and this is where the body gets displaced, and if theta be the angle between them, then work done is always given by Fs cos theta. The product of magnitude of the force and the displacement and the cosine of the angle between them. And students, it is only when the body moves along the direction of the force applied. In that case only, when theta is 0, that work done is given by the product of force and displacement. That's a special case. But actually work done is given by Fs cos theta. Clear? So these are the two vector quantities. Force is a vector quantity. Displacement S is a vector quantity. But their dot product is a scalar quantity. Work is a scalar quantity. So that is the reason why dot product of two vectors is always a scalar quantity, and it is known as a scalar product. Dot product is also known as scalar product. There are some other examples as well. Power. We are aware, rate of doing work, rate of the consumption of electrical energy, that's power. But in vector form, in the terms of dot product, it is also given by scalar product of force and velocity. Now look, this is the dot product or the inner product. Force is a vector quantity, velocity is a vector quantity, but their inner product or dot product is always a scalar quantity. So power is a scalar quantity. Similarly, students, there is a term called electric flux. This term you will learn about it in class +2, right? So electric flux, for the time being, just remember, it is given by the scalar product of electric field and area vector. This is not area, it is area vector, it's a vector quantity. So again, these are the two vector quantities, but their inner or the dot product is a scalar quantity. So electric flux is a scalar quantity. Similarly, in magnetism, you will study that the magnetic flux, this is electric flux, this is magnetic flux. It will be given by the scalar product of magnetic field and area vector. Magnetic field, as you are aware, it's a vector quantity. Area vector is a vector quantity. So again, their dot product or inner product would be a scalar quantity. Magnetic flux is a scalar quantity. So whenever we consider the dot product of two vectors, then its resultant will have only magnitude, and hence it will be a scalar quantity. Clear, students? Therefore, dot product or inner product is also known as a scalar product. There shouldn't be any doubt regarding this. So let's concentrate on some other properties as well. Now let's discuss the fourth property. Students, the dot product of a vector with itself will give us the square of its magnitude, right? So what I have told you is the dot product of a vector with itself. What will it get? Product of magnitude of A. Again, the second vector is also A, and cosine of, these are two equal vectors. So the angle between equal vectors is 0 degree. So it is cos 0. So magnitude of A would be A. This would give us A. Cos 0 is 1. So what do we get? A square. So A vector dot A vector is equal to A square. So what I mean to say is that the dot product of a vector with itself will give us the square of its magnitude. So that is another very important property. Clear, students? Okay. Fifth, suppose the two vectors are perpendicular to each other. This is A vector, this is B vector, and let us consider the angle between them to be 90 degrees. Then what will happen? A vector dot B vector, as per the definition, it will be equal to product of magnitude of A and B and the cosine of the angle between them. Here the angle between them is 90. Cos 90, as we are aware, it's 0. Therefore, A vector dot B vector is equal to 0. Thus, if the two given vectors are perpendicular to each other, then their dot product is always equal to 0. Please do remember it. This particular concept will be used in solving certain numericals. So, the dot product of two perpendicular vectors is always 0. Clear, students? Sixth property. Now let's consider the dot product of two collinear vectors. Dot product of two collinear vectors. Now students, we are already aware of collinear vectors. Collinear vectors are those vectors either of equal or unequal magnitude, and they must be acting along the same straight line, along the same direction or in the opposite direction, or in parallel or anti-parallel direction. So basically, the angle between collinear vectors must be either 0 degree or 180 degree, right? So let's consider both the cases when the angle between them is 0 degree. So A vector dot B vector, in such a case it will be equal to magnitude of A, magnitude of B, cos 0. So it will be equal to AB. Therefore, magnitude of A dot B would be simply equal to AB. Clear, students? Now consider the other scenario, case 2. For collinear vectors, the angle between them may be either 0 degree or 180 degree. So let's consider the other case when theta is equal to 180 degree. In this case, A dot B, it will be equal to product of magnitude of A and B and the cosine of the angle between them. Students, cos 180 degree is minus 1. So we'll get minus AB. A vector dot B vector. Therefore, magnitude of A vector dot B vector would be equal to AB. Clear? So what is the conclusion then? If the two vectors are collinear, then the magnitude of their dot product is always equal to the product of the magnitude of the two given vectors. Clear, students? Again I repeat this very important result. If the two given vectors are collinear, that is the angle between them is either 0 degree or 180 degree, then the magnitude of their dot product is always equal to the product of the magnitude of the individual vectors. So that's the result, right? Okay, now let's discuss the dot product in terms of rectangular components, right? And before that, we need to discuss the dot product of unit vectors. So let's discuss the seventh property, which is the dot product of unit vectors. Dot product of unit vectors. Okay, in the case of rectangular components, students, you are aware, we make use of I cap, j cap and k cap so as to represent the direction along x, y and z axis respectively, right? So this is x axis, this is y axis and this is z axis, right? So the direction of x axis is represented by I cap, the direction along y axis that is represented by j cap and the direction along z axis that is represented by k cap. All are mutually perpendicular to each other. All are mutually perpendicular to each other, right? So let's discuss I cap dot I cap. So as per the formula, A dot B is equal to A into B into cosine of the angle between them. So here it will be magnitude of I again, and these are the two equal unit vectors. What's the angle between them? I cap and I cap. It is 0 degree. So this is a unit vector. We are aware the magnitude of a unit vector is unity, that is 1. So I cap, its magnitude is 1. I cap again, its magnitude is 1. Cos 0 is 1. So it is equal to 1. Right, students? Similarly, j cap dot j cap, it will be equal to magnitude of j cap multiplied by again magnitude of j cap and cosine of angle 0. The angle between these two is again 0 degree. They are equal vectors. So magnitude of any unit vector is always unity. So 1 into 1 cos 0 is 1. So again we get 1. Similarly, if you proceed, k cap dot k cap is equal to 1. So therefore we arrive at a very, very important result, which is I cap dot I cap is equal to j cap dot j cap is equal to k cap dot k cap is equal to 1. This is, students, a very, very important result, right? Do remember it. So I dot I is equal to j dot j is equal to k dot k is equal to 1. I, j, k. These are the unit vectors representing the direction along x, y and z axis respectively. Clear, students? There are some more important results in case of unit vectors, so let's discuss those as well, right? So let's discuss I cap dot j cap. So it is product of magnitude of I cap, j cap and cosine of the angle between them. What's the angle between I cap and j cap? It's 90 degree obviously. Cos 90 is 0, so it will become 0. Similarly, if you consider j cap dot k cap, it will be equal to magnitude of j, magnitude of k cap and the cosine of the angle between j and k. What is the angle between j and k? Again, they are mutually perpendicular, so angle is 90 degree. So it will be again 0. What about k cap dot I cap? Again, these two being perpendicular and dot product of perpendicular vectors is always 0. So here again, we will get 0 only. Cos 90. Angle between k cap and I cap is 90. So again, we get 0. Right? So another very, very important result. I dot j is equal to j cap dot k cap is equal to k cap dot I cap, each is equal to 0. So these are the two very, very important results. Clear, students? So now we are in a position to discuss the dot product of rectangular components. So let's do that. So 8th one, we'll discuss the dot product in terms of rectangular components. So let's discuss the 8th problem. Dot product in terms of rectangular components. Okay, what we do is, let us consider two vectors A vector and B vector, which in terms of I cap, j cap, k cap may be written as ax I cap plus ay j cap plus az k cap, right? And B vector may be written as bx I cap plus by j cap plus bz k cap. Here ax, ay, az, these are the components of A vector along x, y and z direction respectively, while bx, by, bz are the components of B vector along x, y and z direction respectively, right? So let's discuss its dot product, A vector dot B vector. So what to do is, let's substitute the value ax I cap plus ay j cap plus az k cap dot, this is the dot product, right? So what we get is, substitute the value of B vector over here in terms of its components, so it will be bx I cap plus by j cap plus bz k cap. Now let's try to solve it. So let's open the bracket. So what do we get? ax I cap dot bx I cap, right? Plus, yeah, you can write it like this, plus by j cap plus bz k cap. Let's simplify it, isn't it? Plus this term ay j cap dot the same term, that is bx I cap plus by j cap plus bz k cap, plus the third term, that is az k cap dot bx I cap plus by j cap plus bz k cap. Clear, students? So now this is the dot product and ax, bx, these are the magnitude. So dot product is only between vectors. These are the two vectors. So we'll write it as ax, bx, I cap dot I cap. Now in the previous property we have discussed, I cap dot I cap, j cap dot j cap, k cap dot k cap, each is equal to 1. While I dot j, j dot k, k dot I, it's equal to 0. Let's make use of those results in this case, right? So students, look, I cap dot I cap, it's 1. So we'll be left with ax, bx. I cap dot j cap, it is 0. So the entire term will get eliminated. I cap dot k cap, again it's 0. So the term gets eliminated. So from here we'll get only ax, bx. Plus, consider this one. This j cap dot I cap, it is 0. J cap dot j cap, it is 1. So what will be the coefficients? Ay, by. Plus j cap dot k cap, again it will be 0. So from this expression we'll be getting only ay into by, right? Let's consider this term, third term. K dot I, it is 0. K dot j, it is 0. K dot k, it is 1. So k dot k is 1 and we will be left with az, bz. These are the coefficients. So az, bz. So students, this is the eventual answer. So you can make use of it directly without going through these steps. So whenever the two vectors are given in their form of rectangular components, then the scalar product of those two vectors would be always given by the addition of the product of the coefficients of I cap, j cap and k cap of the two vectors, right? So it will be ax bx plus ay by plus az bz. Now you can easily check there is no direction involved in the right hand side. So that is the reason why the dot product of two vectors is always a scalar quantity. This is only the magnitude part. This is only the magnitude part, and hence the scalar product of two vectors is a scalar quantity. This must be a scalar quantity, right? So please do remember this very, very important result. Understood? Okay, let's discuss another property. Students, by using the concept of dot product or scalar or inner product, we can determine the angle between any two given vectors, right? So how to find out the angle between two given vectors? Let's do it. So suppose two vectors A vector and B vector are inclined at an angle theta. So next property is determination of angle between two given vectors. Again, let us consider A vector is ax I cap plus ay j cap plus az k cap. So A vector in terms of rectangular components will be written like this, and B vector is equal to bx I cap plus by j cap plus bz k cap. Fine. So these are the two vectors. This is suppose A vector. Let us consider this to be B vector, and this is angle theta. So how to find this angle if the two vectors are given in their rectangular components? So by definition, the dot product or the inner product or the scalar product of two vectors is given by the product of magnitude of A vector, magnitude of B vector, and the cosine of the angle between them. So from here, cos theta can be written as A vector dot B vector divided by magnitude of A multiplied by magnitude of B. Clear, students? Now let's substitute these values which we have obtained in the previous properties, right? So cos theta. Just in the previous article, we have discussed A dot B in the rectangular components. It will be given by product of the coefficients of I cap of both A vector and B vector, that is ax bx, plus the product of the coefficient of J vector, J cap on both the vectors, that is ay by, plus the product of the coefficients of K cap of both the vectors, that is az bz. That is how A dot B is represented, right? Divided by. Now students, we are aware, if A vector is represented in terms of its rectangular components, then its magnitude, we have discussed earlier, it's given by square root of the square of coefficient of I plus square of coefficient of J plus square of coefficient of K, right? So, what about the magnitude of A vector? It will be ax square plus ay square plus az square. This will be the magnitude of A vector multiplied by magnitude of B vector. It will be bx square plus by square plus bz square, and ax, ay, by, bx, by, bz, these all are the components of A vector and B vector along x, y and z direction, right? So this is the formula to be used for the determination of angle between any two given vectors which are represented in form of their rectangular components. Right, students? So I hope you have understood this, right? So we have discussed various examples of dot product, we have discussed various properties. Now let's start with some very basic numericals, right? So as to prove that dot product indeed obey commutative law as well as distributive law. Let's do that. So let's take any example. So let us consider A dot B, right? We'll prove that it is of commutative, it obeys commutative law. So let A vector is equal to, suppose, 2i cap plus j cap minus 3k cap. Suppose A vector is represented like this, and B vector is represented by I cap minus j cap plus k cap. Clear, students? So to prove A dot B is equal to B dot A, it's very simple. Let's consider left hand side, which is A vector dot B vector. We are aware A dot B will be given by the sum of the product of the coefficients of I cap, j cap and k cap of both the vectors, right? So A dot B, it will be given by its coefficient is 1, so 2 into 1, Ax into Bx, plus Ay into By, its coefficient is 1 and its coefficient is minus 1, right? Plus Az Bz, Az is minus 3, Bz is 1. Am I clear, students? So what we get is 2, 1 minus into minus 1 is minus 1, and over here minus 3. So 2 minus 1, 1 minus 3 is minus 2. Clear? Now let's solve right hand side. It is B vector dot A vector. B dot A. Now here what we do is coefficient of I cap is 1. So 1 into 2 plus coefficient of j cap in case of B vector is minus 1 multiplied by 1 plus k cap coefficient is 1 multiplied by minus 3. So what do you get? 2 minus 1 minus 3. So again 1 minus 3, that is minus 2. So you can check left hand side is equal to right hand side. Okay, now students will verify the property of dot product, which is a dot product obey distributive law, right? So for that we need to consider any third vector. Suppose it is C vector. So it can be written as I cap minus 2j cap plus 3k cap. Let us consider C vector. And we'll keep the same values of A vector and B vector. So in the distributive law, what we are supposed to prove is A vector dot B vector plus C vector. We are supposed to prove that it is equal to A vector dot B vector plus A vector dot C vector. So this is the distributive law which we are going to mathematically verify, right? So for this, let's consider left hand side. Left hand side is A vector dot B vector plus C vector. So first we will consider this particular term, and then we will consider the dot product of A vector and the result of B vector plus C vector. So let's consider B vector plus C vector. Doing the addition of vectors, it's very simple. We simply need to add the like terms, isn't it? This is B vector, this is C vector. So coefficient of I cap is 1, over here coefficient of I cap is 1. So I cap plus I cap, it will give us 2I cap. Minus j cap minus 2j cap, it will give us minus 3j cap. Plus k cap plus 3k cap, it will give us plus 4k cap. Fine, students? Okay, let's evaluate this one. Therefore, A vector dot B vector plus C vector, it would give us A vector, its value is 2I cap plus j cap minus 3k cap dot B vector plus C vector, its value is obtained in the earlier step. So what we write is, it is 2I cap minus 3j cap plus 4k cap. Now let's solve it. I cap dot I cap is 1, I dot j is 0, I dot k is 0. We are aware of it. The dot product of two vectors which are given in the rectangular components would be given by the product of the magnitude of the coefficients of I on both the vectors plus the product of the coefficients of j cap plus the coefficients of the product of the coefficients of k cap. Right? Let's do it. So 2 into 2 plus coefficient j cap is 1. Coefficient j cap over here is minus 3. So it will be 1 into minus 3 plus coefficient of k cap over here is minus 3 and here the coefficient of k cap is 4. So let's evaluate it. It will be 4 minus 3 minus 12. So what do we get? 4 minus 15. So it will give us minus 11. So the numerical value of left hand side is obtained to be minus 11. Now students, let's evaluate RHS, right hand side. Okay, let's consider RHS. RHS is A vector dot B vector plus A vector dot C vector. We'll evaluate the first term and then the second term and then add the two results. Let's get the result. So consider A vector dot B vector. Now let's do it directly. A dot B, we are dealing with these two vectors, right? Coefficient of I is 2, over here coefficient of I is 1. So it will be 2 into 1 plus coefficient of j over here is 1 and over here it's minus 1. So it will be 1 into minus 1 plus coefficient of k is minus 3 and here the coefficient of k is 1. So let's evaluate it. 2 minus 1 minus 3. So it will give us minus 2. Clear? Put this as equation number 1. So now let's try the other term, that is A dot C. A vector dot C vector. These are the two vectors under consideration. The coefficient I cap is 2 and the coefficient I cap of C vector is 1. So it will be 2 into 1 plus coefficient J cap is 1 over here and coefficient J cap is minus 2 plus coefficient of A cap, coefficient of K cap of A vector is minus 3. Over here it is 3. So it will be 2 minus 2 minus 9. So it will be minus 9. Therefore, RHS, which is A vector dot B vector plus A vector dot C vector, it will be equal to A dot B is minus 2 and A dot C, it is minus 9. So what do you obtain? Minus 11, which is same as that was obtained in the left hand side. So students, what we have verified is dot product or inner product or scalar product, it obeys distributive law. That is A vector dot B plus C is equal to A dot B plus A dot C. So students, I hope you have enjoyed this session and you have understood the concepts. And do join me in my next lecture. In the next lecture, we will be discussing some very important and useful numericals related to dot and scalar product. Till then, do take very good care of yourself and bye-bye. Thank you.